such time dependency. Oh, what's happening? Okay. And we observe that such time dependency upon the static structure factor is just a fingerprint of materials, out of equilibrium materials. There are many references of such aging along experimental reports, but another important fingerprint that characterize these systems are the finding of very slow dynamics in the systems, and such slow dynamics are observed actually in structural relaxation times, in the increases, very large increase in the structural relaxation times, or very large increase in the system's viscosity, where Tg is the temperature in which they found the glass transition for such systems. And these are just empirical thresholds for which a very large increase in these properties are expected for the transition towards out of equilibrium states. Sorry. Now, let me tell you about a little bit about the theoretical framework that I will be employing in order to describe these properties that I have just discussed. And we will be employing the non-equilibrium self-consistent generalized Langevin equation theory. This theory actually have two main equations in order to describe the quantities that I just introduced to you, which is the covariance and the mean value of the density. And in these equations, there appear terms such as the chemical potential, which is in terms of kVt, in units of kVt, the stability thermodynamic matrix, which can be obtained just as a simple functional derivative of the chemical potential, the free particle diffusion coefficient, and a dimensionless diffusion coefficient, which we call mobility, which couples both equations, and it is dependent of the distance and time. So we can actually vote of this quantity, at least in its inverse, sort of related to the viscosity, and the fingerprints that I just discussed can actually be observed in terms of, for example, the mobility, which we will be describing in this work. So how do we solve such equations? What we end up doing is, in order for us to solve this couple equation from the mobility, we actually need a set of couple equations which are also given from this theoretical framework. I will be not discussing any further these equations along the presentations, but you could ask me later about them. But these equations actually needs as an input the quantities that we are trying to compute. So what we actually end up doing is like not recursively, but step by step, solving such equations in order to evolve these quantities. And we were talking about this theory which describes non-equilibrium systems. How do we enter such non-equilibrium systems? We enter them, we describe them by describing the preparation protocol of our system, in which, for example, what we are thinking is that we can modify the thermodynamical properties which describes our system, such as the bulk density and the temperature of our system. So the non-equilibrium part of this theory, or how these quantities evolve, are actually in principle describe of how we operate such thermodynamical properties. So by doing some approximations and by stating certain preparation protocol, we are actually able to solve the equations that I just discussed. And in what follows, we shall consider specifically such instantaneous isochoric quenches, such processes such as the instantaneous isochoric quenches, in which we prepare our system in a very high temperature and then quench it down in a state point described by the window frame of our phase diagram. So this is the theory that we will be employing. And now let me discuss how with such theory we can obtain the non-equilibrium version of the equilibrium phase diagrams, which we state as glass transition diagrams. So what we'll be doing is, particularly, we'll be following the mobility quantity along the quenches that we'll be procuring, that we will be doing. So the question will be, what's the mobility for a certain quench along the phase diagram of our system? And in order to follow such quantity, we will consider, for example, mobility is greater than 0. See if we quench, for example, a quench inside the fluid region as fluid, while we're quenching inside the freezing line, what usually one would expect is the transition towards crystalline solids. Nevertheless, in this work, what we'll be considering is that we will frustrate such transition toward crystalline systems. And instead of that, we'll be considering them to be a metastable fluid, to be in a metastable fluid state in which the mobility could be is still greater than 0, or for very specific cases, the system becomes arrested by finding that the mobility is equal to 0. And we will find states such as the glass. So we will be following this quantity, and we will be doing it with a color scheme in which we will represent the mobility, clear colors of the mobility as to be more fluid-like systems, very high mobility values, while darker colors towards purple will be considered as less mobile states of the system. And we can follow them with the equations that we were just describing along time. So, for example, we can follow the transition along time just by following the different colorings in our system. Whereas within the theory, we can actually also describe the states in which B is equal to 0, and we will be doing we will referring to such states as black only when this condition is found. This is actually found only in terms of the long asymptotic values of the waiting time, which will be relevant for further discussions. But we are doing this in such a manner because actually we can follow the mobility along the phase diagrams for a multitude of quenches along the phase. So we can actually zoom up to such region and see how the system mobility evolves just by following the difference in the color for different waiting times, and find interesting regions such as this one, in which what we are observing now is how this region over here slowly evolves towards smaller and smaller values of the mobility. So just like we did in the previous slides, where we just reached the asymptotic long waiting times, we can actually just evolve to such long waiting times and find that the region that was actually evolving pretty slow within the colorings of the mobility is actually found to be arrested states of the system because the coloring just turned black. And what we can end up doing is just follow such region in which the mobility of the states reaches 0. And then what we end up doing is like we can trace the line in which the system becomes arrested by such condition. And this is what we actually refer to glass transition diagrams, in which we can actually separate the systems, the system states in which the system equilibrates and the system becomes dynamically arrested. Nevertheless, as I have stated before, this only occurs within the theory for long asymptotic waiting times. So how do we input the time dependence in such diagrams? Because the thing about the glass transition diagrams that I just showed is that they are actually found only within these such conditions when long asymptotic waiting times are considered. So one of my major contributions in this work was just not doing such ideal transition toward the glass transition line, towards to the dynamical arrested state, would soften a little bit the condition and input, instead of the ideally be equal to 0 condition, just state that the mobility decreases at very small numbers, such as the conditions that I have just been describing that are empirically employed in order to describe the glass transition lines, the transition toward glass states. So what we can actually end up doing is following the condition that I have just stated and end up following the time dependence on the transition of our system when different times where different evolution times are considered, and we do it by following the solid with circle lines, whereas the solid line is just the asymptotic b equals 0 condition. So this line actually ends up approaching and eventually meets within the resolution of this picture the asymptotic line. Oh, strange. And let us know, introduce that this approach can actually, we end up using actually such approach along the whole window frame that I was just showing you of the equilibrium phase diagram. So we can describe actually the evolution. What's happened? That's strange. Can I show the? Sorry, the slides seems to have some problem. Where is it? That's strange. Oh, why it's happening? Okay, never mind. And then what we can actually end up doing is just describing the whole window frame. And for example, there should be a slide between this and the other one, which just describe how does this evolves towards such states. That's why I am like, what's happening? But what we end up finding is that we can actually end up entering to regions such as the spinodal line. And eventually we end up actually also describing the asymptotic long waiting times. And just as like we did before, there will be, we can trace the dynamical arrested states of such diagrams. Okay. And for example, stating that the condition b equal to 0 is actually found to be described just as the line that I have just shown in the previous slide, but then it actually follows along the spinodal line that we were just describing previously. So Okay, here is actually an evolution of the mobility. So by following the condition b equal to 10 to the minus 5, what we actually want to do is to follow the condition, a practical condition for which we can find the transition towards out of equilibrium states. And we can do it along all this, along these phase diagrams. So what? Why is doing that? Okay. Okay. They are missing something. Why? Why are they like that? Sorry, there appears to be some sort of problem because I just made these slides with PowerPoint and we are using Google, so something happened in the conversion, I think, and they are not properly displaying the video. Nothing can do right now.
Perhaps if you have your previous presentation there, the videos look quite well.
Yes, but because we end up presenting it in Google Slides and not PowerPoint, something happened along the conversion. Got it. Elizondo yes. Aguilera. That they looked very nice in the previous presentation, but over here, I cannot show you. Okay. So what we actually wanted to do in this slide is to follow such condition a long time, and this should be a video in which we could stop it, but actually follow the line that I have just showed you. This solid line with circles, and how does it starts to evolve and pass from one state to how to it ends up like meeting the eventually long asymptotic lines. Whereas we can actually evolve further in time and find that within the resolution of the window frame, the condition b equal 10 to the minus 5 and the condition b equal to 0 actually end up meeting pretty well. So what we actually end up doing by following such empirical threshold for the mobility of the system is we end up following the transition towards dynamically arrested states, sort of. So with such idea, what we actually end up doing is that we can describe the dynamically arrested state of the phase transition diagrams in 3 regions. One for fluid systems, in which the system is expected to equilibrate, and it is displayed just by the difference coloring pretty near to the yellow and green ones. And dynamically arrested states displayed in asymptotic long waiting times with the black coloring of the mobility. Whereas we can distinguish by exploring other kind of properties, 2 different regions between the dynamically arrested states of the system. One for gel-like arrested states, which I will be showing later. How can we, what are the sort of difference that we can observe from these states to this one, and one for the glass-like arrested states. This is where the dynamically arrested states meets the spinodal line, and how such a line actually can end up entering along the spinodal line and be followed like this. So this is this sort of line is like a continuation of the glass transition that is found for larger densities. So this was our objective at the beginning, and these are the sort of diagrams that we are trying to describe with the mobility, like I have just described. So how can we do? How can we end up following such diagrams or describing such diagrams? Well, actually, for our systems, we were just describing such cuts along the mobility, but we can actually end up following different planes. And so, for example, we can end up having phi versus time planes, density versus time planes, or temperature versus time planes for different cuts in density or for different cuts in final temperature. So by following, for example, the cuts density versus time for different values of the final temperature, what we actually end up doing is defining such planes in which they are actually pretty close in the description to what the time temperature, between the diagram observed by, for example, Laponet systems. Of course, the systems are have different interactions and have differences along really well, pretty well remarked differences, but still the resemblance it's quite good in what qualitatively what we can describe from the theoretical approach and what, for example, it is observed for the experimental system. So in this plane, by selecting a temperature, we can actually end up observing many of the features that are observed in experimentally observed. In addition, we can consider, for example, temperature and time planes for different counts along the density. And then we end up visualizing the variables such as the ones described in the time temperature transformation diagrams, for which we can actually do a qualitative comparison between the diagrams that are obtained, for example, in the time transformation diagrams of the borosilicate system and our hard sphere plus square well system. Some of what little interpretation that we can do to this data is actually referred in this work, and this is like one of my major contributions of my current dissertation, which can be found along this reference. Now, let me talk to you about other property, which is the density, which we just ignored in the previous slides. So, in order to describe the processes that I have just been describing by the mobility, we will now be describing such processes, but now with this quantity, the density. And why are we going to do that? Well, because what we actually think is that in this quantity, we can observe actually the morphology of our system, which can be visually very impactful and can be very good in order to interpret some of our data that we were just describing by the mobility. So how do we do that? Well, in the approximations that I have previously stated, we were doing this one equal to this one to the bulk value, but how can we not do such approximation in order to solve these equations? Well, what we actually end up doing is we will be considering, instead of solving the whole problem, we will be considering just linear approximations or up to the linear terms of the previous equations, for which we will be computing for this quantity. And where what we actually end up doing is considering and homogeneous mobility for our system states. So what does it happen when we consider such linear approximations? We end up having such equations which we can actually solve, and whose solution is given through this equation, where omega of k and u is just the propagator of the function. And with such equations, what we actually want to do is, this is like an initial state of our system in which we will be describing a volume such as this, but will we be observing in terms of pixels. So each pixel is assigned a density value, and we will be observing right now just a face of the cube. So we want to follow the evolution of these densities that I am just displaying right now, a long time when we are evolving with the previously shown equation. And each of the pixels is actually a square of size sigma, for which we are describing the density. This is our resolution case. We'll be doing this for quenches along the phase diagram. And for example, why this one will not be showing, because it's actually, sorry, I'm having problems with my animations, but this one should be an animation in which this one evolves a long time. And I am showing you, for example, the final state of such animation right now, which is displayed, for example, for a finite waiting time such as this, and an asymptotic length waiting time such as this, where what I'm stating is that, for example, at very large quantities, at very large times, what we end up doing is like, we end up freezing the configuration, and actually what we end up displaying is pretty close to the asymptotic long waiting time snapshot of what we are trying to describe. But let me explain you a little bit of what is happening over here, because we just missed the animation. The coloring dark areas are actually displays of very high density values of the density, whereas the white regions displays are very low values of the density. So what we are thinking with such images is that these black coloring areas are areas of our system in which the particles are concentrated, whereas these regions are empty regions for which particles, for which no particles can be found. So what we end up observing when, for example, quenching a system towards such states such as these ones, is that the phase separation occurs, but it ends up arresting because of the dynamical arrest process that is modeled through the theory. So such a spinodal decomposition process is actually ends up stopping just because the mobility of the systems. This is the inverse of the mobility. So if the inverse of the mobility increases, the mobility decreases. When approaching the dynamical arrested states, such increase in the inverse of the mobility just displays that the systems stop diffusing. The diffusion is very, very, very low. And these such heterogeneities are, for example, observed along the static structure factor by the apparition of very large peaks at small wave vectors such as this one. Whereas, for example, typical static structure factors from fluid-like systems are such as this one observed, in which no large peak in small wave vectors are observed. Okay. So we actually can end up employing the waiting time dependent diagrams that I have just showed you previously by the following the condition. And the next animation will be not shown, but okay. Just by, for example, following such a snapshot such as this one, in which we center each of the proposed processes at the final state of such process. So we can end up following the evolution of the morphologies in such diagrams. Okay, I will pass to the asymptotic waiting time because I cannot, the videos are not working. And what we end up having is such homogeneous states actually represents the equilibration process of the system. So the coloring, the homogeneous coloring is just stating that actually we have this color bar for each of the densities that we are displaying. So each one has been this such color gray in the density in which we are right now. So such display is actually observed just as an homogeneous gray area because as the particles diffuse, you end up losing any sort of memory of the system states. So it becomes homogeneous because the diffusion of the particles just lead towards the disapparition of the fluctuations that we were just describing. But when we enter to states to the states inside the dynamically arrested regions, such as these ones, we can actually end up following different displays depending on where the final states are considered. So, for example, for the gel-like region, which is this region over here between the solid line and the gray line, that we were just showing you in the other diagrams, what we actually end up having is that the spinodal decomposition processes take place, but then at some point of such processes, because of the diffusion of the particles becomes very, very small, they stop to diffuse and they end up forming morphologies such as the ones that we are displaying right now, in which very large heterogeneities can be found for the mean density value of each of the boxes. Okay, and how large they are depends upon, for example, how close they are to the spinodal line. So, for example, when increasing the temperature towards the spinodal line, larger and larger heterogeneity sizes can be found along this quantity. In stark contrast, when observing the glass transition dynamically arrested states, which are displayed for example, these 6 states, what we end up observing is that the system actually freezes up pretty soon in the evolution, and we observe very small evolution from the initial configuration of our system. So this is like a very visual and impactful difference that can be observed between gel and glass-like arrested states. Along such morphologies, there is actually a reference of molecular dynamic simulations in which they actually end up solving the Newton's equations for these particles, such as the one that we are displaying over here. But if they want to follow, for example, the morphology of such systems, what they end up doing is like considering the virtual segmentation of their space, and then they start to describe the densities. First, when they describe the density along the spaces of their system, they can make cuts on the isosurfaces cuts in this quantity. And when what they end up having is sheets such as these ones, in which, for example, the yellow area displays the regions in which small densities are found, and the green area covers up the regions in which large densities are found. And they obtain such isosurfaces for example, multiple states of the system that, which are located in their experimental systems along this region. And within the theory, we can actually end up doing something pretty similar or close to this. This is not the new. Why? Well, I had a new slide, but I don't know why it is showing this one. Okay, I can explain it with this one. In which we, for example, show color. We use a binary coloring of our system, such as white and black, in order to describe such isosurfaces. And maybe later I can show you how we can actually end up doing something in three-dimensional, because I also have such diagrams. It's one of my most recent works. But what we end up showing with these diagrams is that they follow qualitatively the same behavior that they observe in the simulation works. Yep. Okay. So let me finish by stating some summary of what I have just presented. And in general, we can summarize my work in two pretty simple conclusions. We have developed a method which allows us to construct the wearing time dependent non-equilibrium glass transition diagrams, such as the ones that we observe experimentally. And the other conclusion is that we actually were able to characterize the morphologies of dynamical arrested states by following the evolution of the density. So some perspectives of these works are, for example, to follow not only the mobility, but also the viscosity, which it is a recent work within our group. We were recently able to compute for such quantity. So maybe we could use what I have just described for the mobility, but now for the viscosity. That will be like a good perspective in order to start to directly compare with experimental and simulation data. Another perspective is to consider another sort of interaction potentials more similar to the ones described by simulations and experiments. And another perspective is to propose a solution of such equations, but not just for the instantaneous quenching processes that I have just considered, but consider other sorts of processes, such as in which you can vary however you want the thermodynamical parameters of the system. With this, let me acknowledge CONACYT through the grants, Becas Nacionales, La NINFE, and this other grant, which I don't remember the name. CONACYT, the Physics Institute, and the university in general for providing me a space to work and were able to financially support me along all these years. I will also want to acknowledge all my group. This is one of the most complete pictures. There are not all of them, but most of them are over here. Some new integrants are not over here. My advisor, my both advisors, Magdaleno and Luis, for their help along all these works. So that's it. Thanks.
Sorry, I think we can't hear what the other ones say.
Here, the question. Please repeat the question, Mr. Thomas.
Okay. Okay. They are saying me that we should start with Thomas, and I have to repeat the question that Thomas asked.
Okay, I will try. I hope you can hear me. So let me first thank you for the nice
Hello?
presentation, although there were some technical
I'm not hearing
difficulties.
anything.
You're not hearing anything?
No, no, he's hearing you, Thomas, but anyone else in the audience is hearing you.
But
right?
he is hearing me.
He is hearing you for sure because he has this headphones and so on. But the rest of the audience, it's not hearing as much as we can't hear the rest of the
That's
audience.
fine, but okay.
He's hearing you.
Hello?
Yes. Do you hear me?
No, I don't hear anything.
Okay, but Luis, you hear me?
I hear you. Benigno, you can't hear us? If you say no, then you say that's a yes.
Okay, I can hear you now.
Okay.
Okay, good. So thank you again. Very nice presentation. I know there were some technical problems, but this happens to all of us. And I think it's just what the makers of PowerPoint added to test how nervous you are, really. So it's very impressive what you can calculate there. My first question is, where do you think are the biggest challenges of the theory? So what are experimental features that the theory at the moment cannot describe, and why?
Okay, he's asking me what are the most difficult challenges of the theory in order to describe, for example, experimental features, and why. Okay. So right now, at this moment, I will say that the most difficult part within the theory is just to generalize it to other sort of systems, other interaction potential systems, for example, systems such as how are they called, the ones that get energy? I forgot the name.
Active systems.
Yes, so systems such as active systems and so on. I think that right now we don't have any clue how to do such kind of things. I actually want to do such kind of problems, and the difficulty becomes because we have to go back way back to the approximations that we are employing within the theory in order to consider the addition of energy towards our systems. But that's the sort of problem. For example, also to incorporate crystalline like systems, the transition to crystals, that's actually a pretty difficult part for the theory also to tackle. So that would be like two of the most challenging things that I can think right now that the theory is unable to describe at the moment, and it is hard to incorporate to it.
Yes, thank you. The results that you've presented, they refer to the square well system with that is a bit like the Lennard-Jones because it has a large attraction range. What would happen if you considered a very small attraction range?
Well, within our theory, I think we can show sorry. What will happen if we consider smaller or shorter range of attractions within our system, with our range of attractions?
Yes.
And my thesis, or I don't have it over here. Okay, just the glass transition diagram of my presentation. Right now, because we are employing a very unique way to approximate the static structure factor, what we end up having when we do consider a smaller range of attractions is that these lines, qualitatively, they stay the same. But they start to depress and depress for smaller and smaller temperatures. So these lines go down, down, down. And this one also goes down, down, down without any further qualitative change within the expected non-equilibrium phase diagram. So I think that you could actually end up zooming up to a region just similar as this to whatever small range of attraction you want. But we know that some special things actually occur when you consider such a small range of attractions, which the theory right now with such static structure approximation we cannot find.
But you could imagine that you take a structure factor that is better in this regime, and then you would find you would find the glass transition features to change. Can you describe what you expect there? And I'm really interested also in what you expect there to be in the non-equilibrium version of the diagram.
I can only state what it is expected in the equilibrium version, because there is actually it is not a question, it is still the same question he's commenting. But what if you have like a very input, a very static structure factor for the theory? What will happen? What the theory can describe? Okay, so I cannot actually state what is going to happen with the non-equilibrium version, because I think the hardest part is for the static structure factor to actually be able to describe the states. It's not the static structure factor, but the stability, thermodynamical stability matrix to describe states such as this one. But for the equilibrium version, I can recall, for example, a work from Pedro, a reference from Pedro, in which they use hard sphere plus attractive Yukawa system, I think. And they actually end up finding, with a better approximation, I think it's Perkus-Jevic. I don't know. MCA? Okay, MCA. And they actually end up finding the reentrance region and this sort of other theoretical findings that theories such as MCT actually describes.
Yes, that is what I was wondering about. So you have at some point a glass transition.
Okay.
I was wondering what is your expectation? I know you haven't done the calculation, but what is your expectation how the non-equilibrium phase diagram should look like? How would one see the glass transition line?
Right now, I don't have any idea, because I think that I'm not very familiar. Sorry, he's asking me about the glass transition line found by, for example, MCT in such cases. Okay, so right now I don't have a clear idea, because I'm not very familiar with the analysis done by MCT, which is I think I'm not sure about the theory. We have never done such analysis such as MCT in order to describe the glass transition, which will occur over here in the reentrance region.
Yeah, okay, that's fair enough, because it's also speculation, right? You mentioned, however, that one of the extensions of the theory would be, for example, to calculate the viscosity or maybe other mechanical parameters can you explain in more detail what needs to be done there?
Oh, yes. He's asking me about the perspectives, what can be done in order to describe the quantities such as the viscosity and other rheological properties. Well, actually, okay. So for the perspectives, this is a new subject within the theory, but what we end up doing is something pretty, or it's not the same thing, but we end up having the same sort of equations, such as the ones described by Nagel, I think, for the viscosity, in which they use the dynamical properties, such as the intermediate scattering function, in order to describe the system viscosity of a fluid. So what the group end up doing is just generalizing such such derivation in order to be able to be used along the non-equilibrium states. So actually right now, I think that it is just a problem of computing these quantities in a similar fashion as the one that I am displaying for the mobility.
Mm-hmm. And if you look at experiments, at studies on aging of glasses, what are the quantities that are typically measured?
The structural relaxation times, the viscosity, the viscoelastic modulus. That's like the major things that I think everyone measures.
But if you go way back to the 1960s and these old papers on aging in polymeric glasses, they were looking also at thermodynamic quantities, right?
Yes. Which one? If I look up into which one was?
No, I'm just asking. There's old literature on the aging of polymers. And I wanted you to remind us what these people were measuring. Maybe you said it in the beginning, but I think the beginning of the talk was cut off on Zoom.
Benny, one question. Is it possible to just put the audio for the audience, and then you don't have to focus on repeating Thomas' question, but just let them...
We have tried that and it didn't work.
But how about you just put on off your microphone and your headphones, and you just use the audio and microphone of the computer?
Because the laptop doesn't have a very good sound system,
speakers.
audio.
Okay. But still better than nothing, because otherwise you have to repeat to them what Thomas asked you, and then think on the answer, and perhaps it's more easy to not repeat that and just answer close to the laptop, perhaps.
Let me then. How do you change the audio over here? I don't see.
Certainly have to just not use your headphones and microphone, and just use the audio and microphone from the laptop, and then everyone can more or less hear the question.
Well, this one. No. Yes, we can actually do that. Like, you could write and we could all see it. Right now you are on speaker, so
okay,
maybe they will be
able
able
try.
to.
Whoever hears me now. So shall I type?
Okay. I think that what what we do? I'm confused right now.
I mean, perhaps we also just move on with some questions from the local audience, so that we don't get all hung up on technical issues. I cannot hear you at the moment. No.
I think he's not using anymore the headphones or anything else. They're trying to. Okay. And we can't hear those questions as well. We can't hear you, Benny. Can you hear us? We can. Okay. Who knows what's going on? Well, and this is on YouTube right now.
Yeah, but no one can hear it.
But anyway, that was a very nice question. I think Orlando, who is here with us and also can't hear, I bet, he just gave his master's dissertation precisely showing the derivation of similar, actually they were inspired on Gerhard Nagel's work to extend, let's say, to non-equilibrium conditions. And there, actually, what you just pointed out, considering these non-equilibrium ensembles and average and so on, and whether they are time integrals or not. Do you remember that discussion? No, the Swami model work. He just showed how to extend these equations in which you only need the static structure factor and the intermediate scattering functions to compute, let's say, the viscosity of the system. He showed, guided by Magdaleno and Ricardo, how to extend those equations to non-equilibrium. So, and also considering the other question, I think that there are no fundamental barriers to also use similar arguments as in equilibrium liquid theory from, let's say, the knowledge of S or G of R, T, to obtain thermodynamical properties. I'm just saying this because he can't hear us, but he must tell you his view on this thing. But I think that Orlando would be a suitable person to ask this kind of thing. But sadly, it's not his dissertation. And I think they are not even aware that we are not doing anything.
No, they said they are starting with questions from the local audience. Also makes sense. And I can see him answering, so.
And you are right, Ricardo said we are starting with questions from local audience. Now.
Hi, Luis Fernando. This is
Hi,
Leticia.
Hi, Leti.
I think the theoretical approach using the rheological properties, we get a very, very, okay.
Igual y puedes platicar ya desde acá. Si quieres.
I think now we can hear someone.
Hello? Do you hear
Hi.
me?
Yes.
Okay. 77.
There, for example, when you have your tracing, the gray line is the tracing, and the question is, what do you think is happening when the tracing line is reaching the spinodal line?
When freezing line is reaching the spinodal line, you end up the freezing line is just a reference line in which actually the mobility is equal to 10 to the minus 1. So you can actually end up following such line inside the transition for different states. So you can actually end up just like we were following this condition. Just like we were following b equals 10 to the minus 5, you can actually follow b equals 10 to the minus 1. And you end up following the equilibration towards freezing outside the spinodal line. But once it enters inside the spinodal line, because it is reaching an arrested state, it will actually end up converging to the spinodal line, and that's because of the intricacies of the intricacies of the evolution of the mobility, because what we actually expect is, for example, to latency times to occur. So because of the latency times divergence within the spinodal, you actually end up like such both lines end up meeting the spinodal and b equals 10 to the minus 1. But that's all that we can say about it. It is an empirical condition for the freezing, but we don't know if it could be used, for example, to observe crystallization.
Okay. Well, that's all. Adrián? Congratulations. Such a difficult piece of work. In classical coordinates, we know that if we have the partition condition, we know the coordinates. That's a problem to get that. But we know that if we have the partition condition, we know what to do. And we know also that or we have like universal behavior. For example, we know that we will have a critical point. We know that we have a critical point. The susceptibility of the system shows up over the that's for all.
Yes.
Okay. In this case, we show the protocol that we have to follow. And my question is that, okay, we could ask about something like what would happen if we have now a path, or what would happen if we have whatever. You can say that you have to follow a protocol to control the So, okay, you have to deal with some features, problems, and mathematics. If you follow this protocol, you can construct those things. So that the problem is, okay, more about like crafting.
Yes.
So what I would like about if you can have like universal behaviors, even in this case, for example, you show that like it's approaching a different speed in the region. Below the critical point is where the system needs more time to approach. So we think that universal in the sense that if we now change to a different system, would you expect something similar?
I'm not sure. The thing is, yes, they are powerless behaviors, but how to say it properly? Let me think a little bit.
So, for example, in this case, we have like for this diagram perspective, imagine we have a magnetic system.
Yes, what I'm thinking is that, at least for this case, you know that the instability creates heterogeneities within the density, and they affect directly the dynamics. But what I'm not sure is how does the, for example, magnetic sort of system affect the dynamics, and what to expect from for the dynamics of magnetic instabilities of such sorts. I'm not sure.
Because the other part is just like asking about how do you solve this operation? How do you believe? But I would like to know more about the physics of the theory. Something that would be like
General.
useful for explaining what we observe in the classical.
What?
What's the meaning of the second?
It is locally average. You select, like, for example,
But at the end, we saw, I think, implement this delta approximation for the rest.
yes, you could do that, but okay, yes, you could do the delta approximation of the density, but we do not follow this quantity without average because you will actually.
Maybe my point is, this second one, the average n that depends on t. Are you saying that, and you give a number to it, you get a number? Is the number? I don't understand. Is the average or
It's an ensemble average, and it is between all the physical possibilities. Okay, it's better if I.
Are you talking about ensembles in the sense of physics or what?
Of realizations.
Of realization.
Yes, it's better if I do this instead. Okay, with this one. What I am actually trying to measure is that if you, for example, have this quantity which is not an average, but then if you let it go through times, if you don't solve like the Newton's equations, you don't know where the particles are going to be. So you summarize it like saying they will diffuse and they will diffuse. Yes. And then you take what I expect is that there are many different possibilities for the particles to diffuse. That's such realizations of such different realizations are the ones that we are averaging over.
Okay, if you go to the first transparency slide, you describe experiments and clays. That pictures that are over there is have people picture what is happening actually in the experiment.
They do, and visually they only observe like is it transparent or is it become more like
drawings that
they are schematic. That is a schematic. I'm not really sure. They measure the static structure factor, and one could imagine how more or less they arrange because of that.
That is a paper, I think that I think arguments for the
yes.
Those are the correct features. They think this is the correct feature. And from that, you see those experiments and clearly your potential, for example, in the model is completely different. So why do you expect to see something in the physics that is similar?
Just because they have this relation between that they are actually attractive and sort of spinodal decomposition actually occurs also in this system. So just because having a spinodal decomposition occurs, you expect the system to phase separate. That's just the starting similarity, and the other one was because they were observing that gel-like states were formed, and that's what.
At some point, you're going to try to extend your theory to particles and all that.
Yes.
And if you already solved it, and it's similar, and it's the same, so what you're going to do next is going to be the same.
Just to try to be a little bit more quantitative, if you would like to, in order to compare with such experiments, because you cannot be quantitative right now.
Last question. Go to one of your diagrams where you show on this picture how the structure goes. This for the very first. That. Suppose you're in the last one of these columns, the bottom. Are you able to do some sort of pulse in temperature? Let's say that you set up pulse of energy, heat, temperature, just to see what happens. I think about that.
I think we
the system. How stable is in the face.
We can pair two. I think that right now we can pair two. Like that sort of perturbation can be actually be done, but I haven't done. What do I expect? If you input more mobility towards the system, then they will diffuse and start to be a little bit more gray. And depending on how the pulse was given, so for example, if your pulse was high enough in order for it to be inside the spinodal region, then a sort of phase separation will occur. But if it is larger and you go outside to the fluid region, then
so
it
you
will
expect to return to the certain system.
In the returning part, I am not. Eventually, yes.
You need just like a.
Okay, then my expectation would be that it will become more gray in general, because they will diffuse, but then it will stop.
That's when you teach it. That's it. Thank you. Nice thinking.
So let me congratulate you on your license. Work awesome.
Me sacó. What's happening? Do you hear me now? I think
We are hearing you through Ricardo's transmission.
So, all your results, which one would you like to?
Which one would I like the most?
What is the most important result?
Right now, just because we are writing a paper about it, I would say that the heterogeneity is one where like the most
that you like
that I like. But that's because it is my current interest right now. Yes, it would be the heterogeneity part in which I try to physically understand what is happening with such equations.
Regarding the numerical methods, you have proposed ratio with the numerical methods, or
I do think, yes, I do think that I have proposed more than methods, more than proposing numerical methods. I have just used what was already there, but I have improving how they were implemented and taking into notice into small details that previously have not been taken into account in the group.
Some example,
So, for example, one of the most taxing computing tasks that you have to do is make convolution integrals. And they were done, I think that all of our group refers to a very old paper of not Nagel, I don't remember right now, but it's a very old paper of MCT theory, which also deals with such convolution integrals, and they like to separate the time dependence in half and half times. And within our approach or within our theoretical approach, that sort of thing, it is actually not needed. That it only becomes more complex if you try to do it like that. So that's one of the small details. Another detail will be like when you do it carefully, the numerical discretization of such equations, you end up having like you can end up discerning which are the iterative terms and which are not. And if you take into account such iterative terms when you actually try to implement such integrals, you can do it very efficiently because you don't have to compute all the convolution. You just have to compute the iterative part many times, and the rest of the integral is just the same.
Okay, thank you. I think we have time for questions or comments from the advisors. We can write it in the chat.
Gracias. No, yo no tengo preguntas, ya te he preguntado mucho. Es decir, sí tengo muchas, pero van a ir en la cuestión de los artículos que faltan. Por preguntas que se hicieron aquí, son preguntas que nos hemos hecho, son demasiadas preguntas, porque es como reconstruir la termodinámica. La pregunta de Adrián es muy bonita. Si lo sabes, si sabes un protocolo para cuando averiguas papeles de equilibrio, la función de partición, y la puedes estudiar de sus límites, por ejemplo, estos, o digamos probar hipótesis de escalamiento que son muy importantes para entender los fenómenos críticos y todo eso. Aquí, este es el inicio de una historia que está por escribirse en las siguientes décadas, ni siquiera en los siguientes años. Pero nosotros hemos hecho, estamos dando los arañazos iniciales para ver cómo contestar preguntas, pero es que no son nomás esas. Como aquí el tiempo sí entra, ahora también hay problemas de escalamiento con respecto al tiempo. Y el tiempo va a meterse en cuchara, porque los experimentos todos son a tiempos finitos. Entonces, esas imágenes de tiempos infinitos pueden ser relevantes, porque se obtiene, si es a tiempo infinito, pero lo principal se obtiene en un tiempo que puedo ver en el día. Pero hay otras cosas de ahí que nunca se van a poder ver, nada de eso. Entonces, la discusión de dónde entra el tiempo, qué te distorsiona, qué no te distorsiona, es fundamental. Es como estar revisando la termodinámica, pero ahora con el tiempo de ti. Y entonces, lo único que puede uno hacer y está para mí así, pues, ese arañazo de leyes, sin embargo, es espectacular, porque yo nunca había visto un diagrama de fases evolucionarias. Bueno, no lo pudimos ver aquí por razones técnicas. Pero digamos, lo que yo quiero decir, el trabajo de López está muy padre porque te permite, te llevar a diálogo que no tenías algo que ya tienes, que es el puro embrión apenas en la nación. Por ejemplo, los diagramas de fase de temperatura, tiempo, no se parecen, se parecen solo cualitativamente porque el formato es el mismo que el de, vamos a decir, el de los vídeos, ¿sí? Pero la teoría todavía le va a incorporar el hecho de que esos diagramas están hechos sobre la base que la cristalización no existe, que el gas líquido completo no existe. Entonces, si eso no existe, esto sería lo que existiría. Por otro lado, lo que nos enseñaron de estos par de bases es qué es lo que debería hacer si no existiera esto. Entonces, en algún instante alguien tiene que juntar las dos visiones y decirnos cuándo va a ganar Van der Waals y cuándo va a ganar López. ¿Cuándo vamos a ver X o cuándo vamos a ver separación? Yo estoy anotando aquí preguntas que salieron ahorita, pero que son preguntas de una agenda que no se va a acabar. Sin embargo, lo que está muy padre es que cada una de estas tesis nos da un masito más. Pero las preguntas siguen. Y yo lo que quiero también decir es, por cierto, la cantidad de español, con independencia intelectual de una tosudez muy personal, dice las cosas como para él. Sin embargo, por supuesto que ha sido un placer enorme trabajar con Benny, vamos, doctorado. Está dejando una derrama, ya hay 2 tesis de maestría que se presentaron, que no podrían haber tenido la calidad que tuvieron si no ha sido porque capacitaron esta tesis usando el programa de Benny para que estos chicos no tengan que programar durante 3 años o 2 años estas ecuaciones. ¿Sí? Y eso también es otra contribución de Benny. Entonces, nada más quiero felicitar a Benny, el trabajo fue impresionante. Yo soy muy orgulloso, muchas gracias por lo que hemos compartido y por la física que está haciendo. Y eso es todo.
Luis, if you want to talk or say some comments, questions.
Hi, Benny. Comments, of course. Congratulate you for the excellent work you performed. I think it is a highly relevant issue what you addressed, and I think your 2 most, let's say, visible contributions are not minor contributions to the scientific knowledge, but they extend the boundary of our knowledge, and I think that's remarkable. And I again want to congratulate you. I think we already discussed the previous session, the most relevant ones. I think that it's important also to remember that Thomas had at least 2 more questions that you might want to address, and perhaps just to ask, like naively or first, if you think, or how difficult will you think it will be to extend your proposal, for instance, to mixtures, for instance, to a system of particles with different strength or range of attractions, and I mean, if that would be difficult.
It's pretty straightforward, I will say.
Okay, and and perhaps do you think it will be the case as well for the case of non-spherically interacting particles? Like, because there is a version of your theory, I mean, not with the inclusion of the mobility, let's say the heterogeneities that might be like more or less followed at the level of the mobility function. But will you think that it will be also straightforward to extend to systems with orientational degrees of freedom? Because if that's the case, then one can, in principle, answer to Thomas' question, no, regarding the active matter problem, for instance, no, in which you perhaps.
I would think that at least for non-spherical interactions, it will be a little bit more complex. I don't know. I haven't made the work about that. I know that we will have to, for example, take into account a rotational mobility and not just translational mobility. Then you will have also to take into account that you will know we're solving the given matrix due to the translational or rotational mobilities, but I don't know exactly how they will be coupled or if an additional issues will appear if you consider such things.
My guess, I mean, just as a small commercial, is that in the specific case of active matter, starting from a model such as Thomas did within the context of MCT, you might have orientational degrees of freedom, let's say mediated by a rotational diffusion coefficient, but you will not have, let's say, the contributions of the rotational mobility or such an object, because in that case, you might imagine that the particles still are like hard sphere-like interacting, just having these artificial pushes over some well-defined orientation, which is let's say, updated by the action of the rotational diffusion. If that were the case, I think that it might be more or less easy to follow Thomas' work and extend it to non-equilibrium conditions in order to monitor, for instance, the emergence of heterogeneities and so on. But that was just a small commentary. And again, I don't have more questions. I just have a lot of admiration for your work. And I want to thank you in front of the whole audience for letting me be part of your work. And again, congratulations, Penny.
Thanks. So maybe we can go back to Thomas' questions if he wants to finish them. I don't know. Hello? In case you don't hear me. Okay, Thomas says it's fine. Congratulations, also from me, very nice work. So, audience, I think. I would think so. If there is any question from the audience, I think it is open right now. Hello?
No? Okay. Then
We end up the.
we are ending the session. So the jury member needs to deliberate. So please, Christina, cut off the transmission, the live transmission. And I will to ask to all